So welcome back to the number 4 lecture. So let's continue on the planes, and we'll look at also lines in 3D space today. So let's do a very quick review of what we did in the previous lecture. Now we looked at basically the plane equations in 3D space. And the general equation that we have derived, okay, for plane equation in 3D space looks like in this format. And this is a just illustration of the plane. And for this equation right here, as we learned in the previous lecture, there are a couple important information you can immediately extract out of this equation. Number one, the coefficient A, B, C at here. And we call this is the normal vector to the plane. So this is the so-called normal vector. It's perpendicular to the plane. And the second immediate information you can also extract is x1, z, y1, z1. And these are coordinates, okay, for a point in the plane. So this is basically a point on the plane. And this equation here, you can expand it. You can certainly expand it, basically multiply A, B, C into the bracket. Then you can rewrite the equation in a little bit simpler, shorter expression, which will look like this. Right? So your A, B, C is still the coefficients for the equation, except you moved all the constant terms into the right side and then call it a capital D. Okay. So this is alternative writing for a plane equation. Starting from here is always helpful. Okay, so now before we move on at here, I want to test you a quick understanding of this equation. So I'm going to launch an equation question at here. Okay. So I want you to answer this simple question. But be careful, this is a multiple choice. Okay, so basically there can be multiple correct answers. Good, so the plane we're talking about here is 2x minus 4y plus az equal to 15. And we're looking for the normal vector. Okay, the answer is coming in very good. So there's still a few people. Okay, so take part in this question here and see how many of you will get it right. Okay, I think there's still a few answers coming in. That's majority of people, over 80% has answered. Okay, so I'll finish the poll and I'll show you the results. There, this is the results of your choice. majority answered the second one, 2, -4, 8 as the normal vector, okay, to the plane. And which is absolutely correct because you are taking the coefficients at here, okay, directly from the equation to get the normal vector. But the question is, which of the following vector is normal, right? So if you have a plane, how many normal vector would you have to the plane? And the answer is infinite. So you can have an infinite number of normal vectors. They all point in the same direction, maybe actually pointing down, right? The only difference is they are a difference of scale. There's scale difference. So if you look at the first question, this question here, 2, -4, 8 is 1. If I scale it, doesn't matter how you scale, you divide by a number or you multiply by a number, and it's still a vector normal to the plane. So if I actually divide this number by -2, and you will get the third one, which is -1, 2, -4. Right, so that's another possible normal vector to this plane. Okay, so the point here is you could, you don't have to restrict yourself to this. You can always actually pick an easier number, maybe 1, -2, 4. Right? So that might save you some computation effort. Now, for those of you who selected the first one, 2, 4, 8, this is actually a very common mistake that I have seen a student make during exam. Often in time, students forget this negative sign. So they're focusing on the coefficients, but then they forget the negative sign, right? So if you look at the original one here, coefficient here, A, B, C, right? So there are positive in front of it. So the A, B, C could be negative number. So don't forget this negative sign in here. Okay, so otherwise, unfortunately, if you have a question like this, a different question, for example, and you make a mistake like this kind of mistake from the beginning, then you carry this mistake all the way through your question, right? So you'll get, basically you'll get the wrong answer for this, for the rest of the question, right? So make sure that you, okay, do not forget those negative signs here. Okay, very good. So let's continue at it here. Okay, so I'm going to stop the video here. There's a very good question in the chat window. So the question here is to basically to find the equation in the plane, there should be one known coordinates on the plane and the normal vector. That is exactly the point, right? So it's a reciprocal information. Given a plane equation, you can derive these two information. But if you are asked to find the plane equation, then you need to find the normal vector and the points on the plane. Okay, so that's exactly the points you're making at here. So you need these two information to create a plane equation, right? So let's look at one more example here, okay? And then I'll give you have an ample opportunity to practice those things from your assignments and some additional exercise. Now this question is slightly different perspective. So let's see, I have a plane number 1. And then plane number 2. And we're looking for what's the angle between the two planes. And the angle of the two planes, right? So it's always helpful, I think, if you draw a sketch here to help you understand where you are actually looking for here. when two planes, okay, presented to each other, we'll look at shortly we'll look at the geometric relationship, but most probably the two planes could intersect each other, right? So if you have two planes, they may very well intersect each other. And they intersect, they actually will create a line, right, when they intersect each other. Okay. So I guess now the question here is we're looking for is the angle between the two planes. And you can always elongate this. Okay. So that's the illustration of this question here. So I don't know which plane is which, but that's fine. Okay. Yeah. So how do I approach these things here, right? To find the angle. This is basically this angle here. So what you can do is, as I always say, before you proceed, just write down the easy information you can get based on the given question. So you got two planes given. So then I have two normal vectors. I can easily write it down. So you write this down, and it doesn't hurt to draw this on the given plane. So let's suppose this is a normal vector for the blue one, and this is a normal vector for the red plane, not second plane. So once we have this, then you can actually now think about if we're looking for the angle between the two planes, it's actually equivalent, right? If you elongate those two parallel vectors, not the two vectors, normal vectors. So it's equivalent to try to find the angle formed by the two normal vectors. So this theta here is equivalent to the angle between the two normal vectors. So then the question becomes very simple. So because when you have two vectors, and you're looking for the angle in between, so what do? You can use the formula for the dot product, right? So that's basically theta is the arc cosine n1 dot n2, and then n1 magnitude times n2 magnitude, okay, right? So the answer here, you can use your calculator, plug in a number, use your calculator, you will get 1.38 reading for this question. So again, this is kind of, you change your perspective, right? To make use of known condition to get what you want. In this particular case, basically this means the two planes will intersect each other. So that begs actually the question here. I want you to actually develop in a very acute sense of a 3D model, okay, in your mind when it comes to planes and lines. Okay. So what are the possible relationship between two planes, right? So let's think about it. And how do we determine that? That's basically the question here. Again, so let's consider very general situation. Let's say I have the first equation. I have the plane 1 is given by a1 x minus x1 plus b1 and y minus y1 and plus c1 and z minus z1 equal to 0. That's the first plane. Right? And let's say we have another plane, a2 x minus x2 plus b2 y minus y2 plus c2 z minus z2. Okay, there are two planes given, and I can draw the two planes. Okay, draw them out at here. So for the first plane, you have a plane like this, and then you have a normal vector given by a1, b1, c1. And then you have a point x1, y1, z1, okay, on the plane. Let's call it P1. And second plane, so we don't know, so let's just draw this out. N2, P2. So N2, A2, B2, C2. P2 has a coordinate x2, y2, z2. There we go. Okay, so the arbitrary two planes given, right? So how do I determine the relationship between the two planes? So if you think about, oh, I got a question here. Maybe that's a question for the previous answer. Could we use the cross product as well to get an angle? Yeah, I think you can. But maybe it's a little more complicated. It's more computational effort involved if you use cross product for this question here. You can give it a try, right? Because ultimately you're talking about an angle between the two vectors. So good thinking, give it a try, okay? So if you use your two hands, okay, use one hand as one plane and another hand as another plane, just maybe you can tell me now, is that what are the possible geometric relationship between two planes? Number one, easy one, the two planes parallel, okay? And number two, the two planes maybe intersect each other, but at a very special angle, 90 degrees. Okay, good. And these two planes could also be what? Become the same plane, right? Okay, or they intersect exactly at an arbitrary angle instead of a 90 degree. Okay, so those are the relationship between the two planes. So now the question here is, how can I quickly determine, right, which one of that relationship between the two planes? In particular, to look at the equations, right, you can quickly determine some of the actually really special relationship. So here's how you can do it. So let's say for the plane number one, right, you could write the plane number one as A1x plus B1y plus C1z and equal to a capital D1. Second one, okay, it's just changes 1 to 2. Okay. So let's think about the very straightforward. How do I know whether the two planes are parallel to each other? Right. So if they're parallel to each other means they are like this, and the first one N1 and here, and second one and N2 over here. Good. So if these two planes are parallel to each other, and that means N1, N2 must be so N1 must be parallel to N2. Right, so that, or the other way around, it's a necessary it's basically if N1 is parallel to N2, then you can also draw a conclusion that these two planes are parallel, right? Now, what does N1 parallel to N2 means? Mathematically, they are only different by a scale. Okay? So that's what parallel means. Right? So if they are parallel, then they are the two planes parallel. Okay, so no difference. However, as I just said, the plane can be parallel, can also be overlapping each other, all become the same plane, right? So I need to identify that situation, right? So under what condition that the two plane actually becomes the same plane? Okay? So if the two plane become same plane, look at this one here. If if the coefficients is a scale of each other, meaning they're parallel, at the same time, right? So basically, if plane 1 and 2 are the same plane, so that means N1, right? At first of all, N1 has to be parallel to N2. At the same time, your D2, the number D2 at here, should also be a scale of D1. So if these two conditions satisfied, so that means they are the same plane. Okay. So that's how you can tell whether the two plane equations given are the same plane or parallel or not. Good. So now think about the other special situation is that when the two planes are perpendicular to each other, well, it's essentially they intersect with each other. So in this case, what you could do is you can just use dot product. Okay. If the dot product equal to 0, and that means you get the plane 1 is perpendicular to plane 2. Okay. If this dot product is not 0, then meaning they are intersecting by some other general angles, right? So that's how you can identify quickly, just based on the equation. Okay, so there's another question. What is the value of a k here? So value of the k, it's just any number. Depends on the plane equation. You know, for example, maybe if I have a 2x, 4y, and 8z, and equal to 10. And let's not use 10. Maybe use 15. Okay. And then you could have another equation. For example, x, okay, minus 2y plus 4z, okay, and equal to let's say 10. Okay. So for example, right, I have two planes here. So based on what I just actually taught at here, what is the relationship between these two planes? I don't have a poll for this. Maybe you can just chat it, type it here. Good. All right, so parallel. Are they the same plane? Obviously not. You look at the first equation here, the normal vector 2, -4, 8. The second one here is 1, -2, 4. So the key value at here, basically N1, if this is N1, refer to this, and N2 refer to the second one. So N1 equal to 1/2 N2, right? So that's the key value. Okay. Now, because the D value here, they are not 1/2 relationship. So they are not going to be the same plane. They are parallel. Okay, so that's how you can identify. If I change the D value here as 7.5, for example, right? So then these two will become the same plane. Okay, excellent. So that's how you can make use of some of the quick information to identify the geometry relationship. If k is the same, then shouldn't it be d1 equal to kd2 when n1 equal to nk and 2? That's when you have the two planes are the same, right? K needs to be the same on both sides, right? So you're talking about this k here? Yes, the k has to be the same if they are the same plane, okay? Now, if you look at this 15, this 10 here, they are not 1/2 relationship, so they're not going to be the same plane. Okay, hopefully I explained the question here. Is k equal to 2? It depends on how you arrange that. So if I call n1 as 2, -4, 8, and 2 as 1, -2, 4. So what's k, right? So if you write it n1, that's 1/2 n2. If you write it n2, that's 2 n1. Am I right? Sorry. Yeah, sorry, I made a mistake. This is 2 here. This is 2 here. This is 1/2 here. Okay, good job. Excellent. So let's move on here. Okay, I think you have gotten this concept already. I'm now going to do a very quick summary. Okay, for what are the possible type of questions for planes in 3D space. There are many different possibilities. For example, we have looked at one possible question from previous one, and it's a very common one. So what will be a distance from a point to a plane? Right, so think about that, and you will inevitably have to make use that dot product, right? So use a vector dot unit vector, then you get the distance or length of projection. Another type is what we just did. You calculate the angle between the two planes. I can give you a multiple choice question as a quick check, right, in the exam, just to see if you can do the calculation right. And the other general type of question is to find a plane equation. How do I find a plane equation based on given conditions? The possible type of question is, for example, okay, if I give you a point and a normal vector, this is the most simplest question, right? So given a point and a normal vector, try to find a plane equation. So all you need to do is substitute the coordinates point and the normal vector into the plane equation, and you get your plane equation. And the other one, maybe you get a point. Instead of a normal vector, you will probably be given another parallel plane. So basically you got a plane here. This is the question mark, and this is a given. And you also have a point given, right? So you're looking for this plane equation. That's actually very straightforward too, because once you have this given equation, you get a normal vector. And this normal vector can be the candidate for the plane you're looking for. So then you can actually find this plane here. Okay. Another easy one is, let's say you have 3 points given. Okay. And as we learned, geometry, when you have 3 points, it uniquely determine a three-point determine a plane. This is actually how we derive a plane equation. So you could, once you have 3 points, so you can use any one of the points as the point on the plane for the plane equation. But then you can try to find the normal vector by doing the cross product using the 3 points, first forming the 2 vectors first. Good. So another possible type, okay, is that you're given a point, and this is actually we're going to learn shortly, and the line, okay, that is in the plane. So this is a situation. So here's a point here, here's a line here, and with these two, you will be able to determine uniquely a plane. So now the question is, if I have a line, a point, what is this plane equation? Okay, so these two are given, right? So again, the effort is to strive to find the normal vector to the plane, okay? Because you already have a point on the plane, so you can use that point as a coordinate for the plane equation. So the question here is, how do I find a normal vector to the plane? right, for this kind of situation. So as we're going to learn very quickly, okay? So when you have a line given, and you will be able to find the so-called parallel vector to the line. So that's going to be, screw up a little bit, okay? That's going to be quickly can be obtained from a line equation. Is that far enough, screwing up? Okay. Good. So now, once you have the parallel vector here, right? And then you could also find a point on the line, and then you can create a vector between these 2 points. So now you got 2 vectors. Then you can create, basically, move this parallel vector over here, and you can get the cross product of these 2 vectors. So that would be basically a candidate for your normal vector to the plane. Okay, so that's basically how you can solve this kind of question. Okay, so let's say this is P, this is Q, then your N equal to QP cross V or V cross QP, doesn't matter. Good. So there might be a few other different, but I think that this pretty much covers all the possible kind of questions, okay, that related to planes. And we'll also combine lines and plane together as we after learn the line. The other thing before we move on here, and I need you to establish, right, establish a common sense that when you have 2 planes and when they intersect with each other, you end up with a line. So you can just use your hands and you see the end of a line here, right? So the question here is, okay, so now let's bring up to the next topic. What would be the line equation, okay, in 3D space? Okay. And actually, before I move on, I think I'm going to ask you another question in here, okay? Yeah. So let me ask you another question before we talk about the lines. So I'll move this down a little bit here. Okay. So here's a quick question. I'll see if you actually understand this concept. Intersection of 2 planes give you a line. So we'll look at a very extreme case here. So suppose I have a plane, okay, I have a plane of this, and I have another plane, XY. So XY plane basically means in the Cartesian coordinates, your bottom XY here, right, is the plane. And this plane, I don't know how it's going to look like, but it's going to be basically, right, a plane in a 3D space. So the question here is this. Can you find the results of the intersection of the 2 planes? As you can see, the results given here, this is a single choice. There are basically 3 line equations, right? If you look at this, each one of these are line equations in a different plane. Good, yeah. It's also coming in here. Excellent. Yeah. Okay, I think most people got it. All right, I'm gonna end the poll here and share the results. Okay. So this is your answer. Very, very good. So the answer is the last one. So 2x minus 4y equal to 15. As you know, basically the intersection, right, between the two planes is going to be a line. Now, xy plane, right? The thing is, so what's the equation for xy plane, right? The equation for xy plane is z equal to 0. So if you have a xy, that's what represents xy plane. So now you need to substitute z equal to 0 into this plane equation here, and you get 2x minus 4y equal to 15. So that's basically the line equation, right? So this line here is 2x minus 4y equal to 15. Okay, excellent. So let's look at line equation. Okay, now essentially you see when I see a line equation in 3D space, and one thinking is you could just solve the two plane equations, then you can get a line equation, right? But I think that's a little bit too cumbersome if you do that every day, every time. So we need a little more general approach here. First of all, we're talking about line in 3D space. Here's a line in here. And then I'm looking for this line equation in here. So suppose that I have a point P, okay, on the line here. And let's say P is a moving point, right? So P is a point, a moving point on line L. So because P is a moving point, the coordinates of the P, I mean, you can write it as X, Y, Z, right? So I'm purposely left with a little bit of space here. Because a moving point, and basically means as time changes, the coordinates X, Y, Z will change. So I can write each one of the coordinates as a function of T, or time. So now the question basically becomes, what does X of T equal to? And what about Y of T? What about Z of T? Right. If I can find an expression for the three variables, at the same time, the expression will make sure that the point P is moving along this line L, it's like a trajectory. Then whatever I get from here is a description of this line L. So good, right? So this is essentially the objective, right? How to find the line L equation. And this actually brings us a new concept. We're going to actually look at a little more later. It's called parametric equation. So you got three equations here, and each one of the equation is a function of parameter t. So that's why the whole thing here, this set of equations, is called a parametric equation. Okay. I'll show you let's look at one method, okay, to derive this parametric equation. So I'm going to use maybe a specific numbers, and I find often in time, if I just use values, if I use symbols, people don't quite like it. So let's use a number here. So let's say I have 2 points, Q0 and Q1. Okay. Their coordinates are listed over here. Suppose that this is your Q0 and this is your Q1. So 2 point determine a line, right? So I'm looking for basically what will be the line equation passing through Q0 and Q1. So to derive this, let's use the concept of moving point. So let's say I have a moving point Q, okay, along the line L. And I'm going to do some simple assumptions. So let's assume that the Q is moving at a constant velocity. Okay, so Q is moving at a constant velocity here. Then I can represent the Q, okay, with x of t, y of t, and z of t. Okay. So physics, very simple physics. Suppose that at the t equal to 0, Q is at Q naught. So Q start from Q naught. And at t equal to a capital T, certain amount of time, Q is at Q1. Okay. Always remember constant velocity, right? Then at any other time, so at any other t equal to whatever value, t. So Q is Q, right? So Q is on the line. So now I'm going to apply the basic physics formula. Velocity equal to displacement over time. Okay, so that velocity equal to displacement over time. In high school, you know, it's all scalar, right? So you use 3/2, you get the velocity. But once you learn a vector and you know that the displacement and velocity, they are all actually vector concepts. So they can be pointing to any direction. But I'm going to apply this formula here, right? Remember, it's constant velocity. So if I use Q naught Q as a displacement, so Q naught Q, this is a displacement. Okay, and how much time does it take to get from Q? How much time does it take to get from Q naught to Q? Right, from Q naught to Q, how much time did it take? A t. Right? It takes this much time, t. Excellent. And you divide by t, you get a velocity. At the same time, if I use Q naught Q1 as displacement, right? And it takes how much time? Capital T. So you divide by capital T. Right? And both of this give you the same velocity because of constant velocity. So you can let this equal to each other. So now I've actually formed a formula now. So let's substitute the known conditions and also Q, okay, into this whole expression in here. Okay. And I'm going to multiply the small t, okay, to the right side. Okay. So then the left side, Q naught Q, you use the coordinate for Q minus the coordinates of Q naught, which is minus 1. So Q naught is -1 here. And then Y -2 and Z -2. And then I'll put the T on this side here. So the top here, Q naught Q1, I use Q naught Q1, use the coordinate Q1, subtract the coordinates of the Q naught. So 1 minus -1, 2, 3 minus 2, 1, -1 minus 2, -3. Okay, so I get 2, 1, -3, and then divided by the constant value, capital T. So if I expand it a little bit here, basically you have a vector on the left side, you have a vector on the right side. So when the left side vector is the same as the right side vector, okay, then you basically end up with, right, each one of the components of the vector should be the same as the components of the vector on the other side. So I get x plus 1 here equal to 2t over capital T. Okay. And y minus 2 equal to t over capital T. And z minus 2 equal to -3 times t over t. There we go. Okay. And I will simplify this a little bit more because remember, we're looking for the parametric equation, x of t, y of t, z of t. So I will write this specific out for each one of them. So x of t equal to -1, okay, plus this. Okay, so I single out the t here, okay, to make it more obvious. Y of t equal to 2 plus 1 over t, capital T times small t. And z of t equal to 2 plus, no, not plus, this is minus, right? So minus 3 over capital T times small t. Okay. There, so this is basically the result of this question. So the line L that passes through Q0 and Q1 is determined by, can be described by this parametric equation. Okay, any questions so far? Okay, don't see any questions, that's good. So as now you can see here, right? Let's take a second look at here. So there is a constant capital T, which I didn't really give a value, but technically T can be any value, right? So that determines, the capital T here determines the velocity, how fast it goes. You know, smaller capital T, the faster, right? So then maybe what I'll show you now, so if I have t equal to 1 second, then that equation becomes x of t equal to -1 plus 2t, and y of t equal to 2 plus t, and z of t equal to 2 minus 3t. Okay, so that's pretty obvious. But of course, if let's say if t is actually 2 seconds, so then you get x of t equal to -1, okay, plus t, and y of t equal to 2, 1/2 t, and z of t 2 minus 3 over 2t. So different t values, right? Different t values end up with, right? You look at these two set of parametric equations, they're not the same, right? They're not exactly the same. You know, there are some similarities, which we'll explain. But overall here, right, you basically get two sets. You get two sets of equations. But both of the equations, even though they're different, right, they are different. They're different. But both of them right, describes the same line. So different set equation describing the same line. So here's a very important conclusion in here. Essentially, parametric equation for line, right? I mean, you can change the t to any numbers, right? Is not unique. Okay. When you derive a line equation, okay, even for the same line, people can come up with seemingly different parametric equation, but they are actually describing the same line. Physically, what it means is you're describing different motions of the particle, moving particle on the line. Okay, so that's very important. So always remember, right? Line equation, parametric equation is not going to be unique. It will be different, okay, sometimes from people to people. Okay, depends on how you formulate the problem. Okay, so this is the first approach of deriving this line equation out of here. So I do have another approach out of here, okay, which actually a little more simpler to derive this line equation. So give me 1 minute and I'll be able to finish this, okay? So let's say I got a point P naught on the line. X naught, Y naught, Z naught. And for any other point, it has coordinates P, X, Y, Z. I'm looking for the line equation L at here. Okay. So if you have a line equation here, now you can always, actually, you'll be able to find a vector that is parallel to the line. Okay, so maybe going too fast, is that okay? Yeah. Now you can always find a parallel vector V to the line here. So for this approach here, basically, we have given a point P naught and a parallel vector V. Those are the given conditions in the second approach. Okay. So now, if V is parallel to L, I can create a vector from P naught P. That meaning P naught P will also be parallel to the V vector. And when you have two vectors parallel to each other, mathematically, it means the two vectors are only going to be a scale difference. Okay, so now I will substitute all these things over here. Let's say, suppose V, okay, equal to V1, V2, V3. Okay, so that's the given parallel vector. Then on this side here, you have X minus X naught, Y minus Y naught, and Z minus Z naught equal to K times V1, V2, V3. Good. So two vectors, okay, equal to each other. It's equivalent to each one of the components equal to each other. So you get X minus X naught equal to KV1, Y minus Y naught, KV2, and Z minus Z naught equal to KV3. And moving these things to one side, and you have a set of equation, okay, look like this. Now, this is basically, again, the line parametric equation for the line. But this parametric equation now, the parameter here is not T, it's a K now, right? Yeah, so that's the difference. Yeah. But this is still a parametric equation. Okay. And again, it's not unique. Let's say, for example, if I choose a different parallel vector, you can have you can have an infinite number of parallel vectors to the line. Then you end up with completely different equation. And you can also have infinite number of points on the L. So you can change this. You can get another set of parametric equation, right? So we'll look a little bit deeper here to the concept of this parametric equation for line L in the next lecture. But for now, I think what I just did is to show just showed you what does the parametric equation look like, okay, for a line in 3D space. I think I'm going to cover this much for today, so I'll stop video now. And for anybody who's got a question, I'll stay here